In this problem, we have a titration curve for a weak acid with a strong base. There are a few important landmarks on a titration curve. First of all, remember that during a titration curve, at some point, not sure why I circled a circle, the pH will spike or plummet. The midway point on that spike here is going to represent our equivalence point. Okay? Now, when we have a titration of a weak acid with a strong base, there's this region here, again I'm going to circle a circle, where the pH is pretty impervious to change because we have both the conjugate weak acid and weak base present in this portion. So this area here is our buffer zone. Woo! At the equivalence point, we've officially broken our buffer, and then up in this region, we just have a really, really, really basic solution with hydroxides all over the place. Okay, so this part's not going to be good at resisting changes in hydroxide because we're just adding a ton of it in there. So the only buffer zone in this titration is right here. Choice A. This problem is sort of a quantitative-qualitative hybrid question. We can actually answer most of these things without actually doing the calculations here, but we could also do them if we wanted to. So remember, for any weak acid, the general quantitative problem-solving strategy is going to be to do an ICE table. And what I'm going to do here is just set up the general table that you would use here. So if this is 0.3 molar, we're starting with 0 of this, 0 of this. This is minus x, this is plus x, this is plus x, 0 plus x is x. And remember, for weak acids where your K is on order of 10 to the negative fifth or lower, we can make an important assumption to make our lives easier. And that's that this x here really is insignificant compared to the initial concentration of acid. So we're just going to put 0.3 as our equilibrium concentration of this. So let's go through and answer these different statements. Statement 1 says that the A minus, the conjugate base, is substantially less than the amount of HA present. Now, this statement here is going to be true because by definition, weak acids do not dissociate that appreciably. So you're going to have a whole lot more of the fully formed acid. Okay. The second statement says H plus is equal to Ka times the HA concentration and all this to the 1/2. So taking the square root. Well, mathematically, that is how we go about finding the H plus concentration. So Ka is equal to H plus times A minus all over HA. And since these two things are equal, they're both x in this case, what we could do is throw in, we can multiply the HA through. It's equal to x squared. And then if we want to solve for x, we would take the square root of both sides. So, considering that x is equal to the H plus concentration, this statement here is indeed true. And this last statement says the OH minus is much greater than the A minus concentration. Now, this is going to be a very dubious statement here because this is an acid, right? And by definition, in acidic solutions, you're going to have more H plus than, that looks terrible, you're going to have more H plus than you're going to have hydroxide. And since the H plus concentration is equal to the A minus concentration, this statement is indeed defunct. So, 1 and 2 are true, 3 gets the X. In this problem, we have a nuclear decay. Now remember, all nuclear decay is first order, so whenever we're dealing with an initial amount, in this case, The disintegrations per second is reflective of the amount of radioactive material, right? This is like if you had a Geiger counter going doot, 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 doot. It's a measurement of the amount of radioactive material present. So this value up here is going to be our n sub 0, actually. And we're trying to solve for n sub t. So we can use our first order integrated rate law. We have all the information we need here. Rather than plugging in numbers for n sub 0 already, I'm just going to keep these consolidated. And then I'll plug them in at the end. So n sub t divided by n sub 0. The natural log of that is equal to negative 0.693 times the elapsed time. In this case, we have 60 years. Over the half-life. And the half-life is 29 years. Okay, so now we need to get rid of our natural log. So how to get rid of a natural log? Acceptable answers include with an x or with an e. So we're going to take e to both powers to effectively cancel out our natural log. Upon doing this, we end up getting that n sub t divided by n sub 0 equals 0.24. So this is the fraction of the radioactive material remaining. So the question said, what percentage will be left after this time? It would be about 24%, which makes sense because 29 years is the half-life, 60 years is about 2 half-lives. Okay, but the problem wants to know what the activity will be, so now we're just going to plug in for our n sub 0, the 1.2 times 10 to the 12th disintegrations per second. And then when we multiply this through, we will end up getting that n sub t is equal to 2.9 times 10 to the 11th disintegrations per second. Milk of magnesia. It looks milky because there's all of this white solid MgOH2 in its very limited solubility. You can see the KSP is 5.6 times 10 to the negative 12. Well, we want to know here what the pH is of a solution like this. Okay, well, if we're given a KSP and we have to figure out how much is going to dissolve, when in doubt, ice it out. Woo! I-C-E. Solids, we don't care. In this problem, there's no common ion, unlike that problem that we looked at before, so both of these are just going to be 0. Our change is going to be minus x. Again, I like to include the minus x for the solid because this is the molar solubility here. On this side, it's going to be plus x, and for every one of these, we end up getting 2 hydroxides, so we're just going to do plus 2x here. We don't care, minus x is still we don't care. 0 plus x is x, and 0 plus 2x is 2x. Fantastic. So that's 1/2 of our puzzle. The next thing we're going to do is write out our equilibrium expression. So KSP is going to be equal to the concentration of magnesium 2 plus cation times the hydroxide anion squared. We'll plug in our values. So our KSP is 5.6 times 10 to the negative 12th is equal to x times 2x squared. So remember, we have to square both the 2 and the x, so this collectively becomes 4x squared, and then we multiply that by x, and so this all ends up becoming 4x cubed is equal to our KSP, which again is 5.6 times 10 to the negative 12th. So let's divide both sides by 4. And we'll get x cubed is equal to 1.4 times 10 to the negative 12th, and then we will take the cubic root of both sides. So I'm just going to take this value and take it to the 1/3, and we will end up getting that x is equal to 1.12 times 10 to the negative fourth. Now, the question we have to ask ourselves is X the hydroxide concentration? And in this case, no, because the hydroxide concentration is 2X. So we'll just have to take that value we solved for and multiply by 2. So when we do, we'll end up getting that the hydroxide ion concentration is equal to 2.24 times 10 to the negative fourth. This is supposed to be a 4. It just looks like a very bad 4. Sorry about that. When we take the negative log, we'll get the pOH of the solution. So the pOH is equal to 3.65. So the pH is going to be 14 minus that, which would be 10.35. Okay, so our answer is choice D. In this problem, we want to find the strongest reducing agent. So the first thing you should do is recognize that reducing agent means we're looking for something to be oxidized. So we can consult our table of standard reduction potentials, and remember, we're reversing the reactions. So for all of these, we're looking for them to be on the right-hand side, the product side of the reactions given in our reductions potential table. So I'm going to do the first one, and then we'll magically populate the rest of these with their respective reactions. So H2, we can oxidize it to form 2H+, and in doing so, this is giving up 2 electrons. And the E standard of oxidation of this is a standard 0 volts. Okay, so let's go through and figure out the rest of these. Okay, so gold can indeed be oxidized. Yeah, if you've got yourselves 1.69 volts worth of work that you can do. Remember, gold doesn't like to oxidize very much, which is one of the reasons why it's a precious metal. It's stable in that solid form. F2, yeah, we're not going to be able to oxidize F2. Do we see F+? Is that a thing? No, not a thing. Lithium plus is already as oxidized as it's going to get, so this cannot be oxidized. But solid sodium can very readily be oxidized. In fact, this is a very favorable reaction with a whopping 2.71 volts. Since that's our most positive oxidation potential, this is going to be our best reducing agent. Ooh, we've made a voltaic cell. Cool. So our first task is going to be to figure out which side is the anode and which side is the cathode. And to do that, all we have to do is consult the reduction potentials. So over here we have the reduction potential of both copper 2+ and zinc 2+, and then we just need to look for the one that's more favorable. In this case, we can see that the reduction of copper is indeed more favorable, clocking in at a positive 0.337 volts. So this is going to be our reduction reaction, which means we're going to take this reaction right here and we're going to flip it around. So our oxidation half reaction is going to be solid zinc oxidizing to form zinc 2+, and it'll give up 2 electrons in the process. And remember, when we flip one of these reactions, we flip the sign, so now this is going to be positive 0.763 volts. Okay, I'm just going to cross out this reaction here because zinc is not going to be reduced in this particular voltaic cell. So then we can combine our two reactions to get our overall reaction, which is as follows. So here is our overall reaction, and then in order to get the E standard of the cell, we just have to add together the reduction potential of what's being reduced plus the oxidation potential of what's being oxidized. And so our E standard for our voltaic cell here happens to be equal to 1.100 volts. Neat. Okay, but the question is, are we done? Because look at these concentrations here. 0.01, 1.9. Wait a minute, are those standard? No, they're not standard. If they were standard, they would be 1 molar. And since we're looking for E cell, not E standard, it means we're going to need to do a little bit of work here, but not too much. Anytime you want to relate non-standard conditions to a voltaic cell, we're going to use our friend the Nernst equation. So remember, Nernst says that E cell is equal to our E standard, so it's going to come into play, of the cell, minus 0.0592 divided by the moles of electrons transferred in the balanced reaction times the log of Q. So before we do anything else, let's solve for Q here. We can use our overall reaction that we figured out before, and we can say that Q is equal to the concentration of products, which is the zinc 2+. Remember, solids do not factor into our Q expression, over reactants, the copper 2+. So let's plug these values in and see what we end up getting. So our zinc concentration, we're told, is 1.9 molar, and our copper concentration is 0.01. So that means that our Q is going to be equal to 190. Now we have everything we need to answer our problem. So E cell is going to be equal to the E standard that we saw for, that 1.1 volts, minus, and our correction factors are going to be, we've got the 0.0592 divided by, there's 2 moles of electrons transferred in our balanced reaction. So up here we can see we didn't have to do much fiddling around with these. They were fine as is, times the log of that Q that we just solved for, which is 190. So our E cell is going to equal the 1.1 volts minus 0.067. Which equals 1.03 volts. Neat. So this question is asking about how we can decrease the solubility of copper carbonate. So in essence, to decrease the solubility of something, generally speaking, we're looking for a common ion. So choice A is nitric acid. If we were to add nitric acid, actually, since carbonate is a base, by adding in a source of H pluses, they would be able to react with each other. So they could form bicarbonate. And what this would in essence do is take the CO3 out of solution. It would remove it, which means that this, to reestablish equilibrium, would need to shift to the right. So choice A would actually increase the solubility. But choice B is Na2CO3. So that's a source of the common ion carbonate. Whenever you increase the amount of products, that means that this reaction would need to shift to the left, which would be a decrease in the solubility. So this is going to be what would decrease the solubility. NH3 would actually be able to form, because this is a good ligand, it would form a complex with copper, which would remove copper from the solution. NaNO3 sodium nitrate is just an inert solution that wouldn't really do anything here. And then HCl would have a similar effect as A. So B, FTW. Reaction profiles. First thing, we need to see how many steps we have. We have not 1, but 2. Grand. Next, we want to notice that the second step is the slow step. So it's going to be the larger hill. So we're looking for 2 humps here, which means this one's gone and this one's gone. And then we want the larger hill to be the second step. So this one has a small first hill, and then whoa, look at that big activation energy we would need to overcome. So this would indeed be the slow step. Right here's the second one. It looks like this is the one we're looking for. I should have pointed out before too that we're looking for a positive delta G, so we want a net increase in the potential energy, and we can see that that is indeed the case here. We have a net positive change from the reactants to the products. Okay, so choice A is the winner. It seems like there's a lot of A's on this exam, and hopefully there'll be a lot of A's on our final exam. As in the grades, not necessarily the answer choice. So here we're given a weak base Benadryl. Look at it, it's got an amine on it, classic. And we're trying to find the KB. Ooh, that means we're going to do a little reverse icing, which sounds like a delicious type of cake. So we're going to set up our ICE table. It's just in this problem, we're actually given the stuff for our equilibrium line, and then we can use that to find our KB. So we're told here that the concentration of Benadryl is 0.025. With water, we don't care. We love it. And then, so we see here that the pH is equal to 10.7. So that means that the pOH at 25 degrees Celsius would be equal to 14 minus that, which is 3.3. So that means that the negative log of the hydroxide concentration, pOH, that means negative log of the hydroxide concentration is 3.3. So we'll move that negative sign over to the other side. Log of hydroxide equals negative 3.3. And we'll do 10 to both powers. And let's see what we get. The hydroxide concentration equals 5 times 10 to the negative fourth. Cool. Now we have everything we need to solve for KB. So, since we know that that's the equilibrium concentration, 5 times 10 to the negative fourth, well, since there's no extraneous source of hydroxide here, that means that it's all coming from the hydrolysis that Benadryl is creating. For every one of these, we'd get one of the protonated Benadryls. So I'm just going to fill out this whole thing. So the concentration of the protonated Benadryl, the conjugate acid, is also 5 times 10 to the negative fourth. And technically speaking, over here this would be minus 5 times 10 to the negative fourth, but it's really not going to make too much of a difference in the overall concentration here. But this is the reason why we can actually make that assumption that we generally make. So this is going to be 0.0, technically speaking, be 0.02495, but for all intents and purposes, we can just keep this as it is. Then we are going to write out our equilibrium expression. Kb equals the concentration of the products, so the protonated Benadryl times hydroxide, all divided by the concentration of Benadryl, which equals 5 times 10 to the negative fourth times 5 times 10 to the negative fourth. So we can just put 5 times 10 to the negative fourth squared over the 0.025. And we will get that the Kb equals 1 times 10 to the negative fifth for Benadryl. Hey, more Benadryl. Let's see which of these will cause the equilibrium to shift to the right. Choice 1 says dissolving more Benadryl. Well, if we increase the concentration of aqueous Benadryl by adding more reactants, that would cause this reaction to shift to the right. So, yep, this one is indeed ding. The addition of HCl. What would HCl do? Which of these things, either this or this or this or this, is H plus most readily going to react with? If you answered hydroxide, ding, 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 you are correct. So, H plus will readily react with hydroxide, right, to form water, which means that this will indeed cause this to shift to the right. The addition of NaOH, well, that's a source of hydroxide. Now, wait a minute. If we add hydroxide, because it doesn't matter which strong base we're looking at here, if we add hydroxide, that's going to cause this reaction to actually shift to the left, which is the opposite of what we're looking for here. So, wah. And then diluting the solution by adding more water. If we dilute the solution, sure, it's going to dilute the concentration of this, but it's also going to dilute the concentration of both of these products. And water is not going to dilute water. That's just kind of silly. So this has a more pronounced effect for the products because remember that our K is based on the concentration of this times the concentration of this over the concentration of this. So if we dilute this by adding more water, actually this will indeed cause a shift to the right. So which of these is it? It is D, 1, 2, and 4 only.